Okay, good morning, and first of all, I'm really thankful to the organizers for giving me this opportunity to present my work. So I'm going to talk about hydrodynamics of Kyla streamers, and this work is mainly done in collaboration with Professor Frank Urisher, Max Planck Institute Dresden, and my former graduate student Ruma. So I'm particularly interested in certain class of microstreamers. For example, the ciliated microorganisms. They have like different shapes and sizes. So our interest is like how these swimmers move in a fluid, how they interact with each other. So these are the questions that we are asking. So the common feature in these ciliated microorganisms is like this body of the microorganism is covered with hair-like structures called cilia. You can see this animation here. This each one is rod-like structure is a cilia. The cilia moves in a regular pattern, anti-clockwise direction. So already there is an inbuilt asymmetry involved in the system because this the cilia it doesn't move randomly, but rather it moves in a preferred direction. Okay. So because of this synchronous motion of cilia, there is a kind of active force generated on the surrounding fluid. So basically, this is this active force is required to rather they help the body to move forward. Okay. So the question is like some of these swimmers they have only translation motion. That means they move only in a preferred direction. But some of the microorganisms like let's say zooplankton larvae or even this paramecium, they have in addition to the translation motion, they also have a rotation degrees of freedom. That means it can translate and rotate. Okay. So for like probably you're aware of this Swimmer model, which is proposed by Lighthill and Blake long back. So this Swimmer model has been, it's very popular because it's very simple. Let's see, we have just a sphere with radius a, and then there's a slip velocity. But there are limitations with the Swimmer model because the Swimmer model can give only translation motion. But what we are interested in is a kind of a general model which can take care of both the translation motion as well as the rotation motion. Okay. So for that we propose this Kyla Streamer, which is just an extension of the standard Streamer model. So this red one, this is basically a Streamer model. So this will give the translation motion, but this additional term, this gamma and this curl of this spherical harmonics, this will take care of this rotation part. So this is this. This is actually the slip. I mean, like in this Streamer model, this is the effective slip generated by the body. Okay. So the slip is nothing but, see, like when the swimmer is moving in a fluid, so there is a relative velocity between the body and the surrounding fluid. That's the slip. Okay, that's what I'm talking about. And this slip can be expressed in terms of this, the spherical harmonics, where these betas and gammas, these are the slip coefficient, are the modes, you can say. So basically, they control the strength of the slip velocity. Okay. So without solving any like Stokes equations or anything, we can directly compute the migration velocity, the swimming velocity, or the rotation rate of this Kyla Streamer just by taking the surface integral of the prescribed slip. By the way, this is the prescribed slip. In a theoretical model, what we do, we prescribe this slip and then we compute this velocity and rotation rate. So just by taking the surface integral of this prescribed slip, we can calculate the velocity, and then by taking the curl of that, you get the rotation rate. And as you see, that this velocity is the function of these betas, and this rotation rate is a function of gammas. So these two are independent. There is no correlation. So this translation part and the rotation part, they're independent in one sense. Okay. So now, depending on the angle between this translation velocity and rotation rate, this body can exhibit different paths. For example, let's say if the angle is 0, that means V and omega, if they're aligned parallel to each other, then the path of the Kyla Streamer is a straight line, as one would expect. And if chi not equals to 0, like for finite angle, let's say pi by 4, what you get is helical motion, because at every point there is a translation velocity and there is a rotation rate. So the resultant path is helix. So for chi equals to 0, that means if V and omega are perpendicular to each other, then what you get is a circular motion. Okay. Yeah. So without doing anything, we just with the help of prescribed slip velocity, we can compute these basic properties, let's say velocity and rotation rate. But now, if you want to understand the hydrodynamic behavior, that means how two swimmers interact with each other hydrodynamically, then we have to solve the Stokes equation. Okay. So yeah, since this is a Lorentz number, since this is small microorganism, so we can write down the corresponding Stokes equation, where it is the viscosity of the medium, use the velocity field, P is the pressure field. So we can apply the boundary conditions. The boundary condition is, let's say, the velocity field around the body is equal to the slip velocity when r equals to a. That means the velocity field should match the slip velocity at r equals to a. So this is one of the boundary conditions that we can use. And far away from the body, the velocity is 0. That means, if you're in the laboratory frame of reference, then it is 0. Otherwise, there is a finite velocity if you take body reference frame. So we can use the boundary conditions to solve this Stokes equation. Okay, so what I'm showing here is the velocity field. Of course, this is not the complete velocity field, but this is the truncated. I have removed some of the terms which are not required because the contribution from the other terms are negligibly small. So this is from the first mode, and this is from the second mode, and the higher modes I have removed. Okay, this is the simplest one, the simplest velocity field that we can calculate for this chiral Streamer. And as I highlighted, this part takes care of the rotation motion. Okay. So this is the typical velocity field that we can get if we plot this velocity field in different planes. Because this is a three-dimensional velocity field, it's difficult to visualize. So I'm plotting this on two different planes. Let's say YZ plane and XY plane. Here the body is moving along the G direction. So it's moving. It generates these vortex-like structures which are not symmetric. That's because of the rotational symmetry, rotation motion. And on the XY plane, so when the body is moving on G axis on the XY plane, so there is a rotation. Okay, so this is because of this term. Okay, so this is the velocity field. So we can compute these things analytically. Now, once you have all these things, once you know the velocity, rotation rate, velocity field, then you can ask this question like, well, how two swimmers interact with each other hydrodynamically. Okay, so that. But here there's a glitch that if bodies are if swimmers are very close to each other, then it is a bit difficult because we cannot simply superimpose the velocity fields, but we had to treat the problem a bit differently. So what we did was we computed the lubrication force when the bodies are very close to each other. We computed the lubrication force and the lubrication torque. Here, this 2 epsilon is the separation distance between the swimmers, and if epsilon is much smaller than A, then these lubrication forces are effective. Otherwise, they're not effective. Okay, and these lubrication forces they go like ln of omega, ln of epsilon, where epsilon is half of the separation distance. That means only when the bodies are very close to each other, then these lubrication forces come into the picture. Otherwise, they're not. Otherwise, you can simply superimpose the velocity field of Streamer 1 and Streamer 2, and they can solve the equations of motion. Okay, here R is the position of Streamer 1, and V is the velocity of Streamer, and this is the lubrication force if bodies are very close to each other, and this is the velocity field due to second Streamer on Streamer 1. Okay, and here when the body is moving, the frame, this NBT, the body fixed frame, it also rotates. So we need to write down the corresponding equation for NBT.
You have 2 plus 2.
Okay, that'll be done. Okay, so this so we computed this hydrodynamic. We looked into the hydrodynamic interaction between these two swimmers. And here, just to reduce parameter space, what I did was I considered this chi, this angle between V and omega is one of the parameters, and the lambda, which controls the strength of the second mode. Okay, so I'm just playing with these two numbers. The remaining things I set to, I just, for example, I consider swimmers of same velocity and same rotation rate, the magnitude is same, but the angle is not same. The angle chi is one of the parameters I'm playing with. And depending on the angle of, so depending on the sign of lambda, I can have, let's say, pusher or puller. Okay. So this is the diagram, the state diagram. So by varying this chi and lambda with different combinations, let's say pusher, and so on, I get these various behaviors. So here, this is the divergence state. That means initially the swimmers come close to each other, but then they just move apart. Okay, this is kind of a transient regime. And here, this one is monotonically diverging. That means right from the beginning, they just move apart. By the way, here initially the swimmers move. They start on a plane, and then they move. And then they interact with each other. But interesting part is this red one, the square ones. There is a bounded state where swimmers, they exhibit kind of a synchronous motion. They come close, move apart, come close, move apart. Okay, so this kind of motion. This is actually a property of the chiral. Rather the chirality of the system is responsible for this interesting bounded state. And a similar feature, similar bounded state was observed in the case of volvox. Here you can see that these volvox, they also exhibit a similar bounded state, but this system is completely different. We can literally compare these two because this is a bit heavy. 2 minutes.
You need to keep some time for the question.
Sure. I'm almost done. Okay, so the lubrication forces are like, of course, when you consider lubrication forces, swimmers cannot come very close to each other. Okay, that is obvious. And anyway, I think more or less done. So we can also play with the initial separation distance between the swimmers, and while doing that, we can get different varieties of states. And what is important is, if the separation distance is very high, then the boundary states are more favorable. Okay, so that's the message. And with that, yeah, I'm done. Thank you.